No? Okay, excellent. Knew I forgot one thing. So today we have on the plan to look into raster data. Remember last time we talked about GeoPandas, your package extension for pandas to work with vector data. This is kind of one form of geographical data that we typically work with. And then we also looked into Cartopy, the package that helps us with working with different types of projections. Why is it important to have different projections? Because we have a 3D globe that we want to represent typically on 2D surfaces. And when doing so and working with these projections, we typically lose information. But with different projections, we can just choose what kind of information we want to lose or we accept losing. So the examples I made last week was, for example, for a navigation app like Google Maps. You would typically like to preserve distances and angles because these are important features for navigation. And for other things like land eligibility, for example, it's quite important to get the areas right, the area attributes, so that you don't get too big area distortions. What we're going to look into today is rasterio as one package that helps you load and to some extent work with raster data. And then in Atlite, which is one of the tools that we develop here as a group, we're going to work with these two data types, both vector data and raster data, to do our own land eligibility analysis for an example country. And we're also going to look into deriving some capacity factor profiles that we talked about 2-3 weeks back. And we do that now because it's one of the other things that Atlite can do, and also because the land eligibility has a big impact on your conversion from meteorological data to energy systems data, especially if you're aggregating over larger areas. It might be that your best renewable areas are excluded because the terrain is not suitable, or it's maybe natural protection areas. Okay, so that's the plan for the first part of today. And then the second part, it's going to take place only offline, at least I only planned it in this way. It's kind of the consultation hour for the first assignment. As you know, the first assignment is due next Monday. And this is kind of an opportunity for you to ask questions one-on-one. I will walk around, try to help you with any specific issues you have. Yeah, and we'll see how it goes and how many questions you have. But that's basically open-ended until the end of the second session. Good. All right. So let me switch into the notebook for today. As always, you can follow along on the course website where you'll find an identical notebook. And I already talked about the two details, rasterio for geospatial raster data, atlite for converting weather data to energy systems data, as well as doing land eligibility analysis, which I didn't mention here. And what you also have to do, that's not for you to worry about, we'll download one data set here that comes from ERA5. And ERA5 is kind of one of the data providers for weather data. It will give you kind of it will give you a gridded layout of a certain area for a certain time frame. So here for January 2013, for Portugal, of different types of weather data. So things you will see there is kind of wind speeds, solar irradiation, ambient temperature, things like that we'll later use as inputs to convert this data. Right. So just a quick repetition of what we did last time. We worked with GeoPandas, typically imported under GPD. There are typical file formats like the GeoJSON file, a JSON file that has information on the kind of points of a polygon of the country boundaries, for example, as well as information stored on the projection that the data is stored in. We can read that in with a read file a function. We can read that in based on a local file, but also based on some URL. And we can use it pretty much like pandas, setting indices and so on and so forth. So this is going to be useful frame of reference for us later. And just as a remember, this is what it roughly looked like. You have some kind of index, some name. And here we have 2 country codes, like for Vietnam, Yemen, and so on. And then these kind of polygons or multi-polygons, which really just tell you about the points, the vertices of the boundaries. We could plot that and also use the Cartopy CRS package to form something where we actually reproject this data onto a different projection, for example, the Mollweide projection. 2 things that were important here was that, first of all, your axis that you want to plot on, it needed a projection, your target projection that you want to plot in. And then the second important thing is that the data set that you want to plot is actually also given in the coordinate reference system that your matplotlib axis is in. So these 2 always need to be aligned. Okay, so how does it look with raster data? Rasterio, it's completely different, doesn't have anything to do with pandas. It's a bit different, but it's relatively close to NumPy, as you will see in a moment. So one common shorthand for rasterio that you will find is Rio. And the files I also talked about that is kind of, it's image-like. Each cell represents kind of a pixel, and each pixel represents kind of some square on Earth's surface. And these TIFF files, they have, in addition, they're not just pure pictures, but just like the GeoJSON file, for example, they also have data on the projection stored. Also here, you can read from a URL or from a local file. And the command for that, of course, is different in every package, how you open things. But here it's just open is the function, and then you just pass the file name. And I use the abbreviation CLC because that's the data set that we're going to load. If you think back to last week's lecture, we had the Corine land cover, CLC, that told us for different raster cells, kind of what type of land, some classification of what type of land a certain pixel has. So things like forestry, built-up areas, agricultural land, stone, or lake, for example. These data sets, so let's just maybe look at that. It's not going to give you a lot of information. It actually doesn't give you any information other than the file path or the URL that you loaded it from and that you're in reading mode. These objects, this dataset reader, it can have different bands that we have to read in. So an analogy would be, for example, different color bands for pictures. You have something like a red channel, a blue channel, a green channel. I think I mentioned that last time. Or in terms of real data, not related to pictures, but maybe to some geographical data, each layer could represent a different height at which you're looking at, like different cross sections of the Earth. Or it could represent different years. If you have your current land cover, you might be interested in how your land usage changed. Did some agricultural land become kind of wasteland? Did some rainforest become something else, agricultural land? So kind of sometimes you're interested in change, and the different layers are also one way of encoding kind of time series in them. You maybe have one layer for 2015, 2020, 2025. And if we want to access this, we need to read in specific bands. And here again, kind of slightly deviates from Python basic principles. The counting starts at 1, and this data set we're loading actually only has one layer. And then based on this CLC object that we initially opened, we read a certain layer. And what this band is, it's actually a NumPy array. So I can show you that as well. So the band that we read in is just a pure NumPy array. It has a certain shape, like 5,600 something by 3,400 pixels. There are some numbers in them. And minus 128 is not actually a code for a certain land type, but there would be codes 1, 2, 3 to 44 or 42 or something like that that would actually explain, correspond to different types of land. I think I have the table a bit later. The minus 128, does anyone have an idea what it could stand for? Hmm? Borders? Yeah, kind of close, but not quite. So this data that we see here is kind of the edges of the data set, and we have kind of a square. And it's the data set for all of Europe, and most of the boundaries of Europe, they will be somewhere at sea, somewhere where the current land cover doesn't have any data. So the minus 128 is just an indicator for missing data. We'll say, okay, wherever I write minus 128, that corresponds to a missing data value. So here's the um, different value mappings from the different classification numbers and their descriptions to how they show up in the data set. So what they actually store in this raster dataset is not the codes themselves, like 111, 112, 121, but they just count from 1 to 48, 44. So sometimes you have to be careful. You maybe have even a numerical identifier, but this numerical identifier does not correspond to how the values are stored in the dataset. Sometimes you really have to look into the documentation of what value in the dataset corresponds to which classification. Okay. So if we go back to this CLC object, we knew we could read in this NumPy array, this one layer, but there's more to explore in the CLC object. There's data on the coordinate reference system, which again gives you kind of some formal representation of the projection. It will give you things like a bounding box. So what's the coverage of the data set in total? And it will give you the transform. So this is it's just basically the projection. It's the mathematical function of the projection in some way. We don't need to go into too much detail about how that works, but we're going to use this transform for plotting. But you can think of it really just as a kind of mathematical function that converts from the position, the number, or the index of the NumPy array to explicit coordinates in this coordinate reference system. Because based on the NumPy array alone, we cannot work very well with that. Okay, there's a rasterio plotting function that's called show. So again, different packages name things differently. It's not called plot. We can pass the band, so that's just our plain NumPy array, and then pass this function that transforms the indices to coordinates. And then the CMap would be just a way for a kind of different color for a different category here. There's 44 colors, 44 categories. So there will be some duplication in the colors, but I think it shows the gist. So what you get out of that, we're looking at Portugal. You get different colors for different types of land. And here I didn't make the effort to add any labels here. Yes. Uh-huh. They said that 999 is no data. What's the difference between 999 and minus 128? Yes. So, okay, that's a good point. So all of these codes here, these 3-digit codes, they don't show up anywhere in the dataset themselves. It's just a different form of categorization in this core and land cover scheme. But you're right to note this 48 here. And before we had kind of minus 128. So multiple possibilities. So one is I was careless when I created this data set because let's see, maybe I will reconstruct that later. I was careless, did a different cutout, and that kind of extract of the data set because we're loading here not all of it, but just kind of a subset of it. And then maybe I added something that was not in the original data set. And the default no data value is minus 128. It depends on kind of the minimum and maximum values that a certain data type can take. Certain integers can only take values between minus 128 and 127. And the other option is that sometimes you can even, if the read-in function, it doesn't know what the none value should be. And in some cases, you can do things like this. You can say, no, my no data represents 48. I have to assign what code actually means no data, and then these minus 128s they would be substituted. But I don't know if this is actually the exact syntax. But something like that you can see. And it's in principle, it's also not a problem if you have multiple values representing none. You just need to know which ones, basically. Yeah. Okay, so we have kind of a plot with different colors for different categories of land. And again, we have as indices our coordinates in some coordinate reference system. It's actually this kind of equal area projection. Okay, let's also quickly read another file. That is an example of continuous data. So things like you will also find rastered data for the height of the terrain. For example, the SCAPCO data for Portugal, we read it the same way. In many cases, Rio open URL will be sufficient because this function based on the file ending, it will kind of infer what data type I try to load. If that doesn't work, there's always the option to specify a certain driver. For example, I know NC is kind of netcdf file, and I can pass that as a driver if necessary. And the values here, if I just look at the unique values in this NumPy array, they go from minus 3,000 roughly to roughly 2,000. And anything that is minus is below sea level. Everything is positive is above that many meters above sea level. And I can put this in a plot so that we can also build up step by step. Let's see. So let's start with just creating a plot, putting the axes on that and the country boundaries like that. And then we can combine it with this show function from rasterio. Again, we have to pass this, it's always important to pass this transform function. We can set some color map, reds and blues, so kind of blue. I think blues are going to be the ones that have negative values, and reds are the ones that have positive values, and the range of the values. And then we also add a color bar to that. That looks like that. As I said, kind of blue values. You can see where it gets, where of the coast it gets really deep. And you can see some bits of more mountainous area here around the border, northern border between Portugal and Spain. Okay, so we have most of the prerequisites now to work out some of the land eligibility criteria we talked about in the lecture last week. And for that, we're going to work with atlite. Here you can process really both. It handles both vector data and raster data. And the basic principle is that you have something. Remember that last time we had many different criteria and we would like stack them onto each other. And then kind of sum them up in some way or aggregate them in some way so that an area would be excluded if in any of these layers there's one reason to exclude one pixel. And the object that we're going to use to collect the different data sets that we want to consider, as well as their criteria, for example, which types of land to include or exclude, we collect in the so-called exclusion container. That's an object in atlite under the GIS module, and we can initialize that with a certain coordinate reference system. So the coordinate reference system we want to do all our exclusion calculations in at the end, as well as some form of resolution. Do we want to do these calculations at 100-meter resolution, 50-meter resolution, or 1,000-meter resolution, for example? You can tweak a little bit the accuracy. And for example, if you have data sets that are given in different resolutions, say one data set is given at 100-meter resolution, another one is at 50-meter resolution, there are some automatic functions that aggregate or that regrid your data set so that they align, so that the pixels are perfectly kind of aligned with one another. So there's some functions that kind of do that so that you can kind of have the same pixels for every data set that you're considering. Okay, so one thing we talked about natural protection areas. We had this example. I don't know if you did the exercise in the end, but we had this Natura 2000 protection areas. They're given as some form of vector data. Here's a geopackage. And if we want to add this layer and say kind of every shape that is included in this package should be excluded, then we can simply call the function add geometry, pass the URL to this excluder object that we just created. And that doesn't do anything yet. It just kind of logs the criteria that we want to consider in the end. We can use one function here called shape availability to briefly look into what data is being loaded and how that is excluded. It's called shape availability. It's also a function in the atlite GIS module, where it takes two arguments. One is kind of a geometry, for example, a country shape within which we kind of where we are interested in, for example, a country shape. And then also an exclusion container object So that's the one we just created with the different geographical data files logged already. So the first thing we're going to do is we're going to extract the shape of Portugal. The important thing here is that we need that in the coordinate reference system that our excluder object is in. Remember that when initialized, we also gave a projection here, and 3035 is just an equal area projection in Europe. It's only valid in Europe. Isn't valid in Southeast Asia, for example, or South America. And there are other projections than for these regions. And then what we can do is we can call this shape availability function, pass the shape, the country shape, the geometry object, and this excluder object, and that will now kind of calculate pretty much a rasterio object that has kind of value of true when the area was excluded and 0 if the area is still available, and will give you basically the band, so the layer of kind of one rasterio image as well as the transform. Yeah, so just to show you, kind of the band is takes a few short seconds. But anyway, what you'll see in a moment is that the band here will be a NumPy array with some values true or false. Actually, eligible rasters have the value true, and excluded cells have the false value, and that we can plot then later. And we'll also, by using the shape, anything that lies outside of the shape, it will also say it's not eligible because it's not in the scope of the geometry that we are looking at. So it looks like many values here are at the boundaries are false, but if we look at band any, we'll see that there are actually some of them are true, and the transform is just this kind of projection function that we saw earlier. And we can use that together with, together in this rasterio plot show function. This is pretty much as before. We plot here the outlines of our shape of Portugal, and then use the show function with the band and the transform. And then we get green values where there are no projection areas, and then everything that is white and within the shapes are the natural protection areas of Portugal. So if we were interested in kind of land eligibility analysis for Portugal, for wind turbines, then these would be already excluded, kind of would be one layer that we're excluding. But now that if we really want to calculate the area, then we would need to count now how many of these pixels are green. If we just assume kind of natural protection areas are the only exclusion criteria. And we also know how big each of the cells is. We know the resolution was 100 meters by 100 meters. So we know the area is 100 meters by 100 meters. And then we can just count how many cells are true. We multiply that with 100 meters by 100 meters. We get an area out of that that would be eligible. Okay. So that's what we're going to do in this block here, and I'll walk you through that. So the important thing is here, band sum. It just counts, it sums up all the true values, and every true value gives a value of 1. Gives you the number of eligible cells. The cell area is just the excluder resolution. So we put in 100 meters before, 100 meters squared. And then to get the total area that is eligible, we just multiply the two. Cell area times eligible cells. And then we get the kind of square meters that are eligible. In many cases, we're interested in kind of how much % are excluded from these criteria. So what we can also take is we can take the country area, which we have access to through the shape geometry. And and take the eligible area that we calculated and relate it to the total area. So once we do that, so we do eligible area by country area times 100, so that we get something that is given in percent. So we have 79% or almost 80% of the area that is eligible. At this point, it often makes sense to do kind of a visual spot check. Roughly, does it make sense that this is 80% still there and 20% excluded? Kind of. At least it's not inverted, for example, or at least it's not kind of 10, 15, 20% off. So here's a note for Windows users. Sometimes these can be quite big values. Oh. So we have kind of 7 million, and then the cell area is 10,000, of course. And then we have the country area in meters. Oops. Country area. That's an even bigger number because it's all in square meters. And now sometimes what can happen is if you take one big number, multiply or divide with another big number, it can lead to some numerical troubles. My recommendation in this case would, before you do that, convert everything to square kilometers. Basically dividing everything by 1,000,000. You have smaller values to work with and the same level of accuracy for the number ranges that matter. Yeah. So I could also, before doing this kind of in this last calculation, I could also divide everything by 1,000,000 and get a much more lenient calculation numerically. Okay, so typically we're not done with just one data set. The whole idea or core of this exclusion container is that you layer different exclusion criteria. So let's just recreate a new one, a fresh exclusion container. We can add back our geometry of natural protection areas, and then let's add a few more, for example, from the current land cover dataset that we looked at earlier. So now the question is a bit, okay, we have to provide some additional information if we have this raster data, because we have to say what codes should be, kind of what data values should we exclude? Should we exclude, and for example, we might say the codes, the numbers in this raster cell that we want to exclude are 1, 2, 3, 4, 5, and 6. Doesn't mean anything here, but you would basically, in reality, look into this table here and say, okay, I definitely want to exclude continuous urban fabric, port areas, airports, and so on. Yeah, so, and before the function was add geometry, for rasters, the function is called add rasters. Also takes the URL. Before we were done after this, but now we have to provide the codes. So this would be codes that we could pass a list, which we previously built, codes to exclude. We also provide the CRS or the coordinate reference system the data is given in. So that's an important information here, that the CRS here will always be the coordinate reference system that corresponds to whatever you pass here. It's not the target CRS, that we already specified when initializing the exclusion container. We can also specify here things like the no data. For example, here we can say should be 48. And what we can also do, we talked about these buffers around built-up areas. This also takes the argument buffer, and here we would have 800 meters because this coordinate or our target coordinate reference system is also given in meters. So we can do that. Oh, no, almost. Yeah, need to execute in order. And you see here, it's all super quick. Like it doesn't do anything other than logging what future calculations the excluder has to do. And we can do everything also the inverse way. So before we said we have 6 codes that we want to exclude, and everything else can be included in principle if there's not another reason why it should be excluded, like natural protection areas. We can also do it the inverse way. We can give another list of codes to include, like 12, 13, 18, and so on. Again, 6 random codes. You can say everything that does not correspond to these codes should be excluded. We only give a positive list of codes, which works exactly the same, except for one keyword argument that is invert. Because the default is that the codes that you give, they should be excluded. And if you pass invert true, the inverse is true, hence the name, that only the codes you give, they are eligible and everything else is not. So when I execute that and do the same kind of plotting as before, let's hope it doesn't take too long. But I will get, again, kind of another map with green values where all exclusion criteria are not met. Yeah, everything is green. There's no exclusion criteria that speaks against building a wind turbine there. Okay, it's a bit slow today. Used to be a bit faster at some point. Okay, here we have it. You might remember a few of these areas, like these big patches here. These are the natural protection areas from earlier. And then we have a lot more criteria that we included, excluded. Looks a bit less patchy, but as I said, we picked random values, so there's not a lot of like insight into actual wind power potentials for Portugal here. But I think the main kind of insight or main thing to understand here is that you layer different exclusion criteria. You look for each pixel, is there any reason to exclude it? If yes, then it shows up here as a white or as false value in the data. If not, then it shows up as a true value, and that is shown here in green. And then based on the yay or nay of the different cells, you can calculate what the area available is in total. Okay. So what does it mean for the wind and solar time series? Well, say we want to calculate the potential wind and solar generation time series if we kind of build them everywhere where it's possible. And we want to have that value aggregated for all of Portugal. Then obviously the areas that are excluded, we shouldn't take into account. So any kind of wind speeds, any even good wind speeds or solar irradiation in these areas should not go into the weighted average of the production time series. They just don't contribute to the potential. And this combination is also something that atlite does. It's actually the original purpose of atlite to, for each of these eligible cells, actually a little bit coarser resolution, calculate calculate the potential wind power production. So I mentioned earlier this era 5 reanalysis data. So that's historical data. It's model-based, so it takes some measured data as inputs, but in the end, it tries to reproduce the weather patterns that were observed historically. And it has been extended, kind of back extended over the years. A couple of years ago, it was from 1980 to 2020, well, basically whatever year, maybe 2020. And it has been kind of back extended to 1940. The challenge there is, of course, as you can imagine, kind of the measurements, the quality of the measurements and the amount of measurements that you had in the 1940s, 1950s is much worse than you had 10 or 20 years ago. But what you get out of, and this data is also publicly accessible, what you get out of that is things like wind speeds, temperature, radiation data in a kind of grid that is at a resolution of 0.25 by 0.25 degrees latitude, longitude. So it's, this roughly, it depends a bit on where you are on the globe, but it's roughly 25 to 30 kilometers boxes, depending on where you are on the globe. And this is the resolution we'll be kind of working in because kind of for each of these 25 by 30 kilometer cells, we have one value per hour of each meteorological attribute. So how do we load that? Well, first challenge is that this era 5 reanalysis data is global, has now, 85 years, lots of different meteorological data variables available. We need to work with something that in atlite terms we call cutouts, kind of subsets of the full data set that are digestible to work with. For example, a month of data and just a country. So we cut out Portugal, for example. And that is what we initially downloaded. We can read that in, and we get some kind of metadata about that when we look into this so-called cutout object. We can see the X and Y extent, as well as the time frame and the time resolution, as well as the meteorological features that have been downloaded. In the backend, this is all working in Xarray. We're not going to do too much with Xarray, but a lot of the packages that we're going to use, they use Xarray in the backend. The way you can imagine or think about Xarray is that it's like pandas. It's kind of labeled dimensions, like indices and columns, but in infinite dimensions or n dimensions. In pandas, it's a bit difficult to work with more than 2 dimensions. You lose this kind of table layout. In Xarray, it gives you more to work with, basically, more dimensions to work with. For example, here we have the case where we have at least 3 dimensions, X, Y, and the time dimension. And we can always look at Xarray datasets in this way. It gives some somewhat nice representation of the different dimensions, how many values are in the dimensions, what the coordinates are, and what sort of data variables are stored. So what you can see here, for example, as well, the roughness is also a value that is provided in this data set. Remember that we used last week to scale wind speeds to the hub height. So we'll have kind of higher values where there's a lot of braking effect from the wind speeds. Okay, let's quickly plot the grid. So we can access the grid with cutout.grid. And you can see now you get a bit of feeling for what level of resolution we're talking about. it's much, much coarser than the 100 by 100 meter resolution that we looked at earlier. It's kind of, I don't know, maybe 100 or 150 cells for all of Portugal. So that means you have kind of 150 data points of wind speeds for each hour. And yeah, so that's the level of accuracy we're working with here. And we can access the different data variables, for example. When we say cutout data and we access one of these attributes here, for example, wind at 100 meter would be just the wind speeds at 100 meters in meters per second, I think. We can access that and we get kind of what the dimensions of that are. Here we actually we did something, we already reduced the time dimension, said we want to calculate the mean, and in pandas we would have said, do we calculate the mean across the columns or across the rows? In X-ray we would say we calculate the mean across a certain dimension, and we have to label the dimension by their name. So we aggregate by time, and could, for example, plot that just on a 2D raster and see kind of higher wind speeds offshore, lower wind speeds in the mountainous area. And if we apply the same kind of laws that we looked at last time, we actually have all the data that we need to do that. Kind of say we want to scale the 100 meters wind speeds that we have down to 10 meters using the log law. So this mathematical equation here before. The Z would be our 100 meter, our 10 meters. The ZR would be the measured data, the 100 meters, and the Z0 would be the roughness that we also have already in the dataset. And just like with pandas, we can combine the different attributes, different variables to calculate the wind speeds at 100 meters and then get scaled wind speeds. So everything that you know from kind of NumPy, pandas, that you can run functions, multiply different objects with one another, the broadcasting, everything is basically the same. Sometimes you have to be a bit more careful about the dimension names and so on. So we have to be careful with the dimensions. Say, for example, in a previous data set, we aggregated across the time dimension. Maybe we want to aggregate along the regional dimensions, so we can also build the average of across all x and y coordinates. And then you can see how the only dimension that is left is the time dimension. We can access one of them, the influx direct, so the direct irradiation, plot that like we would do with pandas, and get a time series from the same data. You can see here just the daily peaks, some days more sunny than others. So one problem that we still have to resolve somehow is that this land eligibility calculation that we had earlier, it has totally different resolution than the raster cell that we're working with. So, and when we want to calculate, well, how much weight should one of these weather cells get, we would look at what fraction of this area is actually eligible for building wind turbines or some other form of energy conversion. So we would basically take each of these cells and look at within the cell how many raster, like what fraction of raster cells has a true value, and then we get maybe in one cell we have 25% eligible, in another cell we have 50% eligible, and so on and so forth. We don't need to do that manually. There's a function that does that, whereas previously we calculated this with the shape availability function. There's something that's called availability matrix, takes exactly the same arguments, but then does another step. It actually calls the same function, shape availability, internally, and then aggregates each of the small grain true false values into fractions of land eligibility of each of the bigger cells. Yeah, so when I plot that, and that was, yeah, and this is basically taking this availability matrix A for the country of Portugal. So what is log in pandas, for example, is called cell in X-ray. We get now something that has different shades of green depending on what area of this cell is eligible. It actually does something more. Um, um, because you have different cases. You have cells that are completely inside the country, and you have cells that are maybe kind of partially kind of at the border, partially inside the country, and partially outside of the country. So in this aggregation, atlite would treat everything kind of all the fraction that is outside of the shape also as all false values. Makes sense because you're interested in shape, so everything that lies outside of the shape should have zero contribution to the potential. Okay, so and based on that, we know again what the area of each of these bigger cells is, and we know what fraction is available, so we can just calculate a total area available. And there's some magic here going on about kind of restacking a little bit, and I don't really expect you to work through that. Because it's a bit complicated and didn't find an easier way. But I show you the final result. So what I did in this calculation is basically the calculation that we did earlier, like calculating the square kilometers available in each of the cells, and then multiplying it with some assumption about how dense can we deploy wind turbines there. We say we can build 2 megawatts per square kilometer, and then what we get out of that would be kind of some values of in megawatt capacity for each of the cells. For example, here 223 megawatt in one of the cells. Yeah, so that's maybe that. The important thing is that this matrix, this capacity matrix, we're going to use as weights for the power production profile. So we calculate basically for each of the different cells. We calculate now, we basically apply these wind turbine power curves that translate the wind speeds at hub height into a power output, or at least a kind of per unit power output, a capacity factor, and then multiply that value with the total installable capacity so that we can get an estimate of what the energy or electricity production potential is in total if kind of if all the potential were exploited. And for that, we have to use this capacity matrix as a weight when we aggregate this data. What we want in the end is kind of one time series for all of Portugal. So we're really just using the capacity, the potential capacity, for building a weighted average of capacity factors that we calculate for each of these different cells. What else do? We provide a turbine type. So here, a Vestas V90. The kind of scaling of the wind speed at 100 meter that we have given to the hub height also happens internally inside this wind function. And as index, we pass here the index of our shape. So that would be the shape of the of Portugal. And when we execute that and plot that, what we get out of that is it's really simple. Wind.plot. We get the specific or the generation potential in megawatts for all of Portugal aggregated uh, in hourly resolution, in the native time resolution of the model. I think, and I didn't test that before, so it's always a bit risky, but I think you can also do per unit. And in this case, you get kind of normalized values, normalized capacity factors, but that are still weighted by where you can build how much wind turbines potentially. Of course, we can also do that with PV. And here I'm just going to use the same capacity matrix. In principle, you maybe have different eligibility criteria for PV. But here, instead of turbine, you provide the panel. Here, a crystalline silicon panel. What you also give is now an orientation. And the orientation kind of could be south, east, or west oriented. So that's the azimuth angle here. So 180 degrees would mean south oriented. And then also the slope, so the kind of inclination from the ground. And one good rule of thumb for a good inclination angle or slope would be the how many degrees north you are, basically. So it makes sense to have your the more north you get, the more it makes sense to have kind of more inclined PV panel. But just to show you, we can do the same, and we get kind of our PV production profile. Again, we can say per unit true, and plot that as well. And then we get the normalized values here as well. Okay. So that was a run through rasterio and the basics of atlite, where you have both the land eligibility calculation and the time series calculation. Of course, there are a few more exercises that you can go through. The first one is just to change a few of the numbers and buffer distances and see for yourself how the land exclusion changes. And then there's another exercise that lets you play a little bit with the PV function because there's also functionality to have the keyword arguments to have tracking, like horizontal axis tracking, vertical axis tracking, and both axis tracking. And you can see how your energy yield improves from that. So these are kind of exercises that you can do at some point, or either in the next session or at home. I would stop the recording now